Elad BARAM from Emza Visual Sense.
So I'm Elad from Emza Visual Sense. We have named this talk tinyML Journey because it is really about a journey of implementation, but going from the real idea and concept up to a real deployment. And as you have been hearing in the other sessions, in the state of the tinyML today, it's really putting a brick over brick and building the wall step by step. So I think it's an interesting story, and we're going to share a lot of the experiences and difficulties that we have along the way and how we overcome it. 30 seconds on who we are. So been around for a pretty long time. Company established in 2006, doing computer vision and the edge all the time. Last 4 years, focusing on ultra low power in the IoT space, and we develop and sell ultra low power computer vision solutions, end-to-end solution, hardware, software, algorithms, everything. We were acquired by Himax Technologies. Himax Technologies are also sponsors of this tinyML, and they have another session. So we are working in a tight collaboration with Himax. So our journey really begins in CS 2019, just a bit, two years ago, a little bit more. And that was the point where actually Intel announced the Project Athena. And the Project Athena was really about bringing the next wave of innovation into the personal compute space. And this slide actually taken out of their kind of launch event. And you can see that there is a lot of human understanding, artificial intelligence, extending the battery life. So all of those are kind of calling out for some sort of a tinyML ultra low power solution. And we thought that there is a great opportunity actually to bring a lot of value to the personal compute platform if we can bring the right technology into it. So the first step was actually to map out how does the landscape looks like. And what we have been seeing is that if you look on the x-axis, kind of how intelligent the sensor is, and the y-axis is the sensing power and the compute power, we saw that on the sensing side, most of the sensors were pretty simple. Time of flight was the most sophisticated one back then. And all of the other more complex use cases were basically enabled by software solution that were using kind of high power consumption, both on the sensor. They were taking HD vision images and were taking a lot of compute power as they were running out of the main processor. And on top of that, they were running out of what we call the non-private domain, meaning that user has to opt in to the fact that they are being pictured all the time. And our thinking was, can we extend the boundaries of sensing in a way that we will deliver much more intelligence, but under the milliwatt scale and under the privacy domain? So user will not be being pictured all the time, but we still can get face detection and face orientation and deliver value under those restrictions. And what are the use cases that were perceived? So the first one, for example, and speaking again on personal compute over laptop, the first experience is basically can it wake up and wake up like a magic, meaning that you just walk to the laptop and it's automatically wake up. It's detected the user is actually approaching it, and combination with Windows Hello, which is the authentication mechanism, you have a completely touchless login experience without any friction. By the time you sit on your chair, it's already waiting for you to start working. And another one is user presence. So the computer can understand that the user is in front of it and actually be much more responsive. And the next one is walk away lock. So this improves privacy and security. As you walk away, most of the user never change the default setting of 5 minutes. So you walk away and basically the PC stays on, and then anyone can get into it in that time frame. But also if you understand that the user has been walk away, so you can turn off the display and saving a lot of power. So those were kind of the first use cases, and I'll try to have a video here running. Let's see if it generates like a 15 seconds video. And here we are already a year down the road into our journey. This is in Suite in CS 2020, where you can see that I was kind of stepping into the room. The laptop detects me and automatically I'm being recognized. And this shows basically the wake-on approach, how you can just, by the time you sit down, you already can start work. So it's a very cool and innovative experience. But we didn't really wanted to stop here. So the challenge was, can we take this to the next level and enable contextual privacy? And when I mean contextual privacy is a system that actually understands its surrounding and can proactively do some action. So for example, the intruder alert, if we can detect one face, maybe we can detect another face. And if someone is speaking behind my shoulder on the display, the laptop can actually understand it. And then it can drive some action. Maybe it can blur the screen, maybe give a warning, maybe dim the screen. But the beauty of it is that now the system is so intelligent that it can actually drive actions without the user asking it to happen. It's really about bringing the context understanding into those systems. And another use case that was kind of heavily pushed by the industry is the adaptive dimming. So the concept here is that, as everyone knows from personal experience, when you're sitting in front of your laptop, you're not all the time engaged with the content. So the concept of engaged user versus not engaged user. I mean, maybe you go to the kitchen to grab a coffee, or you're just doing some texting or reading a paper or speaking with a colleague. Apparently, a big chunk of the time that you are in front of the laptop, you are not really engaged with it. If you're kind of aggregating all the times that users are not engaged with the content, and you're leveraging this knowledge to reduce the illumination of the display, that provides a big opportunity for extension of the battery life, if you can do it in a private manner and if you can do it in low power. So that's basically the feature named adaptive dimming that kind of came to life, but that requires much more sophisticated classification, because this is not only about face detection. You have to understand the orientation, and that makes things much more complex. Now,
hi, Elad. If I can ask a question on the previous one, and this is Evgeny here. Hello from California.
Hi, Evgeny.
Yeah, quick question. The 20% is very impressive, but I was thinking that users can use other type of sensors and modalities to activate your device. You can touch a keyboard, you can touch your touchpad to wake up the laptop or your computer.
Yeah, of course, if you touch, of course, if you touch the keyboard or something, which people today are kind of used to, because this is the reality. So sometimes if the laptops, if the power policy turns the display off, and now you are looking again on the display, it's kind of off. So you are kind of having this mouse movement where you're kind of shaking or touching something in order to waking you up. But in a frictionless kind of experience, the minute when you turn your face back to the display, it pops up again to life. So it's actually pretty cool when you have it without any interaction. It just like my ideal is that it should work like a magic.
No, I like the use case. I'm just thinking that the 20%, because there are other type of ways you can interact, right? But definitely, I mean, the bigger the better for the vision. We both like it.
Yeah. So that's going to be maybe one of the only slides that's going to touch a little bit onto the hardware here. So the way to
Elad, I had another question on that while we're here. So the privacy issue with people standing behind you, what about on a plane where people are looking at your screen potentially from the side? Is there anything you can do with that? That's one question. And then the second question is where I have multiple screens, right? So I've got my laptop in front of me. I've got a screen to either side. How's it going to work in that usage environment?
Yeah, okay. So this is actually two very different kind of domains of answers. So the first one is really related to the field of view. And I'll show it in the next slide, but basically we are using the field of view of the native camera of the laptop, which is typically 70 degrees. So as long as the face as the other face are within the field of view, and you can actually see them, so then we can detect them. So that's with regards to how wide it is, which is pretty wide actually, 70 degrees horizontal. field of view. Now, with regards to working with external monitors and so on, so that's also something that we are working now with the ecosystem to enable kind of the multiple display, but that also will require some cameras that are within the display itself, which is happening actually with the acceleration of the COVID-19. So I think that we are seeing more and more monitors that have their own cameras, and then once you implement these type of algorithms inside the monitor, so you can get the benefit of having those features working even in a multi-display environment.
Okay, thanks.
Now to the implementation itself. So what you see here is the camera module. So in every laptop on the top of the bezel, there is a camera module. And our idea was, can we add a tiny chip right next to the camera? And that chip will be a milliwatt scale chip that would do an always-on inference. And the image here is pretty realistic because what this chip is WiseEye is getting is a subsampled of the image, kind of a monochrome, low resolution image, and all of the inference is being done on that. And to protect user privacy, there is actually no image output interface. Hardware-wise, the only thing that goes out of this inference chip, from the computer vision chip, is I2C metadata. Basically said, is there a face, 1, 2, where they are looking for, and so on. So only metadata stream is going out, and image actually never leaves the camera module. I mean, as long as the user is not opening the camera. So it's actually working, I would say, out of the camera pixel, but it's working as a visual sensor, and there is no any option actually that the image will ever leave this hardware, this piece of hardware. So that's kind of, it was architected in a way that it will get the image out of a secondary interface of the CMOS sensor, and will not generate any images out. The chip itself, it's called WiseEye. It's actually WiseEye 1, being developed together by Emza and IMAX. There is another whole talk on the chip. I won't get into the capabilities of this chip, but it's pretty unique piece of hardware that enables us to make these type of detections in a milliwatt scale. So, I mean, one can say, okay, so I'll just do some sort of a face detection and I'll have the application running. But in reality, we had many issues to overcome. So first is the distance, the field of view, and the speed of execution. Extremely hard to get this kind of triangle, all the requirements going together. We have an issue of what we call faces in the wild. I'll show some images of what makes it so complex, and the engagement level, what is engagement level, and also dealing with real life illumination condition. We have put to ourselves kind of a high level spec for the detection, which you can see here, which is basically detection 25 up to 200 centimeter, which is about 1 to 6 feet. From 1 foot up to 6 feet with a 70 degrees field of view. And we wanted to be able to run at 8 to 10 frames per second because it's an interactive system. I mean, you blur the screen, you dim the screen, so it needs to be very interactive. So actually the response time is very critical. And we also wanted to have bounding boxes. And what you can see here in the picture is that the difference in size of the faces between a user that is 1 foot from the display to 5 foot to the display is huge. And this brings a problem which we call kind of working in multiple scales, which is very hard to do in microcontroller. Now, it also became clear that we need to move to a detectors and not just with classifier. We needed the bounding boxes because we wanted to understand user location. We actually wanted to have a tight bounding boxes around the faces because when you have a tight bounding box, you can have a good distance estimation, which is also important to the context understanding. And we wanted to do some tracking. We wanted to do some advanced classification. We wanted to do a lot of stuff. We couldn't find a way to actually properly run on this specific tiny chip, an SSD or a YOLO type of detector. We had to come up with something else. And again, we tested, there's not too much time, but I just say that we tested a lot of framework and, you know, mobile net, and we kind of do a lot of trials and error in trying to kind of overcome the FPS, the field of view, and the distance requirement. Eventually, we came up with what I would call kind of a micro computer vision detector pipeline. And the idea is that there are two stages. The first stage for the detection is working on a very, very fast algorithm, which is based on a classical ML, which basically is a kind of generating proposal boxes. You say, okay, this places in the area, this is probably a face. There is a high probability that this is a face. And it can work on multiple scale and cover all the different distances. And once you have those kind of areas that you actually want to process in a deeper way, then you go into a neural network structure. So you do the classification, and here you can do many things. So you can actually leverage the strengths of the network, but computational wise, it is much easier to run the first stage under a classical ML framework that has a much faster rejection rate than running the neural network on multiple scale. So again, short movie, we kind of putting all the pieces together, and we feel pretty good about ourselves that, you know, the application is working, and we can detect the face and the yaw and the yaw angle, and everything works fine. And then COVID-19 is coming, and suddenly what we realize is that all the people that are evaluating the system and working with the system, they all wear facial masks. And we didn't have any people with masks. I mean, no one had people with facial masks before COVID-19, right? And so there is kind of, I guess each company back then had its own kind of COVID-19 crisis response team. So we have our own, which was generating thousands of images with people with masks. So it kind of was a massive data science, because you couldn't find any. There was no public data set or something like this. Most of it was based on augmentation with, you know, data scientists knows that, I mean, it has its strengths, it has its weaknesses. We had to generate a lot of, I mean, this is a topic for a talk by itself of generating data for COVID-19. Now, another thing, and again, this is kind of the difference between how easy it is to make a demo and how hard it is to make a robust system, is that we realize that in the data set that you take, usually people are kind of, you know, standing, smiling to the camera, everything is like visible, very, very nice. But in reality, when you're taking images of people for hours and hours in front of the laptop, they would go like that and cover their mouth and roll angles like I'm doing right now. So the roll angle are becoming, and this actually degrades significantly the ability to make detections. So another response team on the data science on the company was actually to generate enough robust data to be able to cope with the variety of the what we call kind of the natural user posing. I guess this is the last one on the challenges, but one of the toughest one is actually the illumination condition. So people tend to think that the challenge around vision is on a dark condition, but the reality is that actually CMOS sensor can deal pretty good with darkness. The real problem it's the HDR, it's the dynamic range, and we've put some examples here. If there is a strong backlight behind the person, then you see that the faces are completely dark, and it's very, very hard to make a detection. You can barely see the facial landmarks. And on the other way around, if the person is sitting in a dark room and the only illumination is coming from the display, so actually the faces are all white, and it's very hard to make a detection as well, because it's wiping out all the facial landmarks. So it's not really about the lux condition, it's really about the dynamic range. If you have a strong illumination from the side, it's also degrades significantly. Now, maybe I just say 30 seconds here is that people tend to think on images like from their experiences over the iPhone. But when you're working as a sensor, you do not have those fancy ISPs and image stitching and getting image composition for different exposure. You are working, you don't have an ISP. We are doing the ISP by itself. So we had to develop a control loop over the sensor that will actually optimize, will be optimized for detection and be able to cope better with those harsh illumination condition. So 2 years into this process, we are getting very close to production, and you can see this is a real. This is how it looks in real life, and you can see the WiseEye chip here. This is kind of the brain under the tip of the pencil, and this is the sensor. It's also, I don't know if you can see it on, probably the video is showing me as in a very small box, and the module is so small, but this I'm trying to get this closer to the camera. This is, I think it's kind of amazing piece of engineering, both from software perspective, hardware perspective, like this is a real example of tinyML that is going into a high volume production. And last slide in this presentation is that I don't think that we are in the end of the journey. This is actually the beginning of the journey. So in terms of evolution, we can see that tinyML can bring a lot of value to consumer devices and consumer application, not only to industrial. Making demo is easy. Getting it to production and robustness is very, very hard. And you're encountering a lot of issues with data that you have never foreseen to start with. But we do believe that we are in the early days, because with the advancement of more advanced silicon process and new silicon IPs and new algorithms, we'll be able to do much more in less power, which will increase significantly the adoption, because we'll be able to do much more sophisticated things in a much more robust way. So just looking, I think that the horizon is very, very good for tinyML and low power vision in the personal compute space, and probably in many other verticals. So that's basically concludes my presentation. Thank you.
That was great, Elad, and very impressive again. Congratulations. It's going to be interesting technology when we get it on our phones and PCs, laptops.
Again, just a quick shout out to our sponsors. Bear with me for 1 minute. We have different categories. We have executive sponsors. First one being ARM. Then we have Qualcomm. We have Samsung. Platinum sponsors. Ada Compute. Lattice Semiconductor. Gold sponsors. BrainChip. Babel Labs. DSP Group. Edge Impulse. Emza. Gray Matter Labs. Greenwaves. Himax. Imagimob. Latent AI. Maxim Integrated. Quixo. Reality AI. SensiML. Silicon Labs. Sentient. Google TensorFlow. XMOS. And lastly, silver sponsors, Edge Cortex, Hotchi, and Synsets.